Hi everyone, so today's lesson is going to be on something called the natural base E. We're on page 310 in the textbook. So where does E come from? So E was discovered by a mathematician whose name was Leonhard Euler. It looks like Euler. That's how I was pronouncing it for the longest time. And then I realized, and then I forgot what class it was. They're like, no, it's Euler. So this is Leonhard Euler. He calculated its value to 23 decimal places. And E looks like this. It's a cursive E. That's how we're going to see it in our calculator. And in problems, it's just a cursive E. So E, what's so special about it? Well, E is irrational. E is also transcendental. This means it's not algebraic. It's manufactured. Its properties have led to it as a natural choice as a logarithmic base. We'll discuss this later. We'll discuss this more later in the week. So tomorrow's lesson is going to be on natural log. So E is going to be part of the natural log. We'll discuss that more tomorrow. And E is also known as the natural base. Again, we're going to cover that later in the week. And then when most people hear of E, they think of exponential. And that's what we're going to talk about today, exponential. So we're going to cover some more, little more background, how to get E on your calculator, and then we're going to dive into exponential. So E, when we type that in our calculator, we're going to get 2.71828 repeating. Now, when I like to do it, if I'm using just E, I always like to go to at least 3 or 4 decimal places. So how do we get E on the calculator? Well, if you have the graphing calculator, either the TI-84 Plus, the TI-83 Plus, whatever TI you have, as long as it's the graphing calculator, E is going to be above the division sign. So how do we get E? We're going to do second and then the division sign. That's going to put E on the calculator. Once we do that, since E isn't just, when we're using E, it's always going to be raised to some form of an exponent. So to raise E to any power, we have to use the little caret button. And what I like to do is, if it's E to just say a number times a number, simplify that first, because remember, when we do anything to the power of, we have to close our parentheses. So if you don't feel like opening parentheses, simplify the exponent before you go and put it in the calculator. Also, if you don't have your graphing calculator at home, there's this great website. It's called Desmos, and they have a scientific calculator. So if we go to that website, and that website is under the resources section of Plus Portals, you're going to see this calculator. It's going to have 3 different modes. So it's going to have the main mode, the ABC mode, and the function mode. So we're going to have to make sure we go to the function mode, or the function setting. And in here, you're going to see the E to the X. So as long as we click on that, over here in this blank spot over here, an E is going to appear, and then it's going to have the cursor up here, and it's going to be blinking. So to input numbers, you have to go back to the main spot and enter your numbers from that way. So there's 2 different ways to use the calculator. Basically, when we're doing anything with E, use the calculator. So it has to be in the function setting if you're on the Desmos Scientific one. So let's practice evaluating the following. So when we see E, E is always going to be associated with some type of exponent. So E to the 3rd. So we're going to do second, the division sign, and then we're going to hit the little caret button, and we're going to put 3. So E to the 3rd is equal to 20.085, and it keeps going on. So if I tell you guys to round to the nearest 100th, that's 2 decimal places. Now, a little background for rounding: 5 and above, you round up; 4 and below, you keep it the same. So 20.085 rounded to 2 decimal places will be 20.09. And now let's try this one. We have 2 times E to the negative 0.53. Okay, so when we have any number in front of E, what I like to do first and what I recommend you doing too is do E. So do second division sign to get E. So do E to this first. So do second division sign, the little caret, and then type in negative 0.53. Now you're going to hit enter. We're going to get an answer. Now multiply that answer by 2. When we do that, we get 1.177. Rounded to 2 decimal places is 1.78. So how can we use E in our everyday lives? Because you might be looking at this and be like, okay, what do I need E for? Like, how does this apply to anything? So can anyone think of any way we can use it in our everyday lives? Do you ever hear of something called exponential growth, exponential decay, population growth? We can also use it. We're going to cover this later in the week with interest. Remember how last week or 2 weeks ago we had talked about compound interest? Well, there's something called simple interest or continuously compounded interest. Now we're going to learn a new formula for interest, and that new formula is going to have E in there. So E kind of appears in many different aspects of our lives, pretty much on a daily basis. And the examples we're going to go over today with these problems, some of them you can use them, apply them to healthcare, apply them in science. Like this example over here. Basically what we're going to be doing this whole entire lesson is exponential growth and decay. In this particular graph over here, it was the doubling time of E. coli. So we want to know after how many hours is the E. coli basically going to double in size, or not double in size, the amount of E. coli is going to double. That's the biggest example that we use for exponential growth and decay. When I was in college, that's what we did. We grew a petri dish with E. coli, and then we were counting how many were there after X amount of time. So in this graph over here, we can see that it's pretty much steady for a little while. And then after a certain amount of time, it skyrockets. This right here is what's known as the exponential growth. So it basically doubled the amount that there was there in just like that short period of time. After the doubling goes on, you're going to basically reach, it's going to kind of flatten out, and then the decay is going to happen. The decay can be just as fast as it grew, or it could be a little slower. So when we talk about exponential growth, it's going to just basically skyrocket. It's going to grow really, really fast in a short amount of time. So for today's lesson, we're going to think of E as a universal constant for how fast you could possibly grow or decline using a continuous process. So when we think of E, it's going to be exponential. And what I mean by exponential, it's basically continuously growing, continuously compounding. Whatever the problem is, it's going to just be continuous. So it's going to build up on itself. So the first example, the chicken pox is beginning to spread in a small city of 10,000 people. After 2 days, the number of people with chicken pox is modeled by the function Vt is equal to 10,000 over 5 plus 1,245 times e to the negative 0.97 times t. So what's nice about all these exponential growth problems is that there's no one set formula for you guys to remember. Each of these problems is going to have its own formula given to you. So whenever we're going to deal with exponential problems or exponential growth, exponential decline, there's always going to be a function or an equation that goes along with it. So for this particular problem, I want to know how many people will be affected initially. And initial time is always going to be 0. So if I ever say to you, how many or how much money do you have initially? How much will there be initially? It's always going to be equal to 0. And then I want to know how many people will be infected with the chickenpox after 5 days, and then how many people will be infected with the chickenpox after 2 weeks or 14 days. The most important thing here that you guys have to remember is you're just going to have to pay attention to what, for this particular problem, they said time is in days. So your T has to be in days. You couldn't say example for here, 2 weeks, you'd have to convert 2 weeks to days. Why? Because t is measured in days. So the way we're going to do this is, I kind of like to set up 3 problems. So we have the equation that we're going to use here, and remember, we're not using any other equation besides the one that's given to you. And then I set it up because we wanted to know how many people initially, or 0 days, how many people after 5 days, and then how many people after 14 days. Now you notice in the equation we have the variable t. That's the only thing that's going to change for each of these 3 time frames. We're just going to go ahead and plug in 0 in for t, then 5 in for t, and 14 in for t. So if we want to work with initial first, so I want to find out how many people were initially infected with the chickenpox. So what I'm going to do is, I'm just going to go wherever there's a t, I'm going to go ahead and plug in the 0. And remember this VT over here, that's just basically telling you the amount at that given time period. So you're not going to worry about moving from either side of the equation. This just sits here just to tell me, okay, I'm measuring it at this time frame. All of our math that we're working with, the entire problem is right here on the right hand side of that equal sign. So after 0 days, what we're going to do is we're going to plug in 0 for t. So we're going to be left with 10,000 divided by 5 plus 1,245 times e to the negative 0.97 times 0 power. Now what I'd like to do first is I will multiply negative 0.97 times 0, and I'm going to get 0. So then what I'm going to do in my calculator is I'm going to do e to the 0 power and get that answer. E to the 0 power gives me 1. Now I'm going to multiply 1245 times 1. After I get that answer, I'm going to add 5 to it. And then I'm going to do 10,000 over 1,250. I do that in my calculator and I get 8. So initially at V0, at 0 days, there were 8 people sick with the chickenpox. Now this is our final answer for 0 days. Now we want to know how many people were sick with the chickenpox after 5 days. So what am I going to do next? Next, I'm going to take the 5 and plug it in for the t. Do the same thing, 10,000 over 5 plus 1245, e to the negative 0.97 times 5 power. I go ahead and I multiply negative 0.97 times 5, and I get negative 4.85. I then go ahead, e to the negative 4.85 power, get that answer, multiply it by 1,245, get an answer, add 5, and then I do 10,000 over whatever that answer was, and I'm left with 677.96. Well, since we're dealing with people here, you can't have 0.96 of a person. It's just not possible. So what you have to do when we're talking with people, humans, when we're talking about animals, you just can't have a part of a person or a part of an animal. You have to have a whole person, a whole animal. So what we have to do is we have to round this. So I like to round to the nearest whole number. So 677.96 rounds to 678. So after 5 days, 678 people were infected with the chickenpox. Lastly, I want to know how many people are infected after 14 days. So I do the same exact thing. Instead of using 5 now, I'm going to use 14. So it's the same formula. We're just changing the t every single time. So we go ahead and multiply 0.97 times 14, and we get negative 13.58. Do the same thing. E to the negative 13.58 power, get an answer. Multiply that by 1245, get an answer. Now add 5 to that answer. Then we're going to do 10,000 over whatever this answer was, and we're going to get 1,999.36. Well, remember, because we want to know how many people were sick, What we have to do is round this to the nearest whole number because we can't have 0.36 of a person. So the nearest whole number would be 1,999. So there would be 1,999 people with the chickenpox after 14 days or 2 weeks. So our final answers would be for 0 days, 8 people have chickenpox. After 5 days, 678 people have the chickenpox. And after 14 days, 1,999 people have the chickenpox. So we can also use this to measure how much drug's in a patient's bloodstream. So when a certain medical drug is administered to a patient, the number of milligrams remaining in the patient's bloodstream after T hours is modeled by the equation. D of T is equal to 50 times e to the negative 0.2 times T power. I want to know how many milligrams are in the patient's bloodstream after 3 hours. Like I said, what's nice about each of these problems is they all have their own formula. So just say for this example here, chickenpox, how many people had it? We use this formula. How much drug's in a person's body after X amount of hours? We're going to use this particular formula for this problem. So I go ahead and I rewrite the equation. So I want to know how many milligrams of this particular drug are in the body after 3 hours. Where are we going to put the 3? The only spot to plug a 3 in is this T up here. So we're going to do 50 times e to the negative 0.2 times 3 power. Negative 0.2 times 3 gives us negative 0.6. Remember, what I like to do is do e to the negative 0.6 power, get your answer, and now multiply that answer by 50. Once we do that, we get 27.44 milligrams. As always, here is our pet of the day. This is your classmate Kristen's dog. This is Pandora. Here Pandora is sitting enjoying the outdoors. She's got her sunglasses on and she's sitting in front of her bamboo. So some daily reminders. Your homework is assigned daily and it's posted on Google Classroom and Plus Portals. Your homework is to be uploaded to Google Classroom or emailed to me before the start of class. If I do not receive it prior, it's considered late and you will not receive full credit. On Friday, May 8th, you will have a quiz on the material covered so far this week. And as a reminder, on Tuesday, May 12th, your test packets are due back to me. Please don't wait until the last minute to go ahead and hand this packet in. This is worth 60 points, so this is basically worth 2 quiz grades. If you guys have any questions, please be sure to email me and I will get back to you. Have a great day, guys.